Yeah, Assalamualaikum and hello. We are from Group 1. So, we are assigned to do the compressor. So, my name is Maizato Akmal binti Mahat.
My name is Muhammad Iqbal bin Abdul Ghaffar.
My name is Nurul Anis binti Nur Azlan.
My name is Nabila Maheshwaran.
My name is Teo Junha, and so I'll be presenting the schematic diagram of compressor. And as you can see from the diagram, it consists of inlet stream, outlet stream, and work done stream, where external force is applied to compress the air.
So we move on to the function of compressor. First one is to increase the pressure of the fluid. Next one is to compress the gas to very high pressures. The next one, in refrigeration system, the compressor works to circulate the refrigerant in the system under pressure. In gas turbine engine, the function of compressor is to supply air in sufficient quantity to satisfy the requirements of the combustion burners. For industrial chillers, the compressor is used to take in low pressure refrigerant vapor from the evaporator and compress it. In oil and gas industry, compressor is used to provide gas pressure required to transport gas with pipelines and to lift oil in gas lift operations. And the last one is in heat pump, the compressor works to circulate refrigerant between the indoor evaporator and outdoor condensing units. Next, we move on to the real-life application of compressor. Example 1 is when the compressor is used in engines. The compressor functions to increase the pressure of the air to provide conditions favorable for combustion and expansion of the hot gases through the turbine. Without a compressor, the engine could never develop steady thrust. Vehicle engines contain air compressors for heating and cooling, as well as in air brakes for larger trucks and trains.
The second example of compressor is heating, ventilation and air conditioning system. The compressor is the core of heating, ventilation and air conditioning system's cooling function. System's air conditioner is fundamentally a refrigerator that cools and dehumidifies the air well within a building, maintaining cool and comfortable environment. Compressors are found in all air conditioners, notably window and portable air conditioners, and they aid in heat transmission to heat our home. Next, heat energy is transferred from an enclosed location to the outside air via an air conditioner. To cool, the system pulls the heated air from the house through return vents and over the evaporator coils. The extra heat must be removed from the house in a certain way, and that is where the compressor comes into action. The entire heat transfer cycle is performed by the photo-driven compressor in an air conditioning system, which is placed in outdoor air conditioning unit. Air conditioners are composed of two natural phenomena. One would be that heat is transferred from a high temperature to a lower temperature environment. Another is that gases transfer from high pressure location to a low pressure area at all times.
And now, moving on to the third example is jackhammers. So jackhammers is a pneumatic device, a tool that makes use of exceedingly compressed air as its energy source. Typically, it's a diesel engine drives the air compressor, which then forces the air through a hose to the stop device. Well, in this example, it's a jackhammer. So in this diagram, it shows how the jackhammers really work. And so the air compressor is a piece like a massive bicycle that in no way stops blowing air. So when the employee presses down at the handle, air pumps from the compressor into the jackhammer through a valve on one side. So I would like to show a video of how really jackhammers work, so we could get it clear of how it works.
Compressed air goes into a chamber, and a pile driver pushes the bit into the concrete to break it up, and then there's a valve that flips. This compressed air then sends the pile driver back and the bit back up, and that just keeps going in kind of, it's called a self-reciprocating motion. This happens 25 times a second.
So that is all for the jackhammers.
Next, we have example for application of compressor in the system in the compressed air energy storage. The system is commonly found in the turbines. Compressor works to compress air to be stored as an energy in the storage chamber. It operates by compressing and expansion of fluid in the liquid piston. The liquid piston is used compared to a solid piston because it is better in terms of efficiency and power consumption. Compression of air leads to the rise of temperature while absorbing the heat generated during the process promotes the efficiency of compression. Compressed air is then allowed to flow through the vessel to drive generator, which results in producing electricity.
So I'm going to explain about question 4. So refrigerant 134A enters an adiabatic compressor as saturated vapor at negative 24 degrees Celsius and leaves at 0.9 MPa and 60 degrees Celsius. The mass flow rate of the refrigerant is 1.2 kg per second. So determine the power input of the compressor and then the volume flow rate of the refrigerant at the compressor. So this is the schematic diagram. So we have the inlet stream and outlet stream. So here we know that it is a single system that is a steady flow. So the mass flow rate is constant. So for statement, the temperature is T1 is negative 24 degrees Celsius. We know that it is a saturated vapor. So we can get the pressure saturation in table A11. So it is 111.37 kPa. So the H1 value is 235.94 kilojoule per kg. So state 2, the temperature is 60 degrees Celsius and the pressure is 900 kilopascal. So from table A12, it know that the T saturation is 35.51 degrees Celsius. So T2 is greater than T saturation. So state 2 is the superheated vapor for the refrigerant 134A. So from table A13, then we get the H2 is 295.15 kilojoule per kg, and then the kinematic viscosity to 0.026146 meter cube per kg. So here we use the energy in equal energy out. So W in plus mass flow rate times H and mass flow rate times H2. So here we use this equation because it is the stationary system. So kinetic energy and potential energy is 0. So we substitute all the value and we get 71.052 kilowatt. And then the second one is we use the formula mass flow rate equals to density times volume flow rate. So at Z state 2, we know that the kinematic viscosity is 0.026146 meter cube per kg. So as I said before, it is a steady state. So it is the mass flow rate is constant. So we substitute the value and then we get 0.0313752 meter cube per second. So that is all for the question. So here is the reference from all the examples. Thank you.